is Astronaut Giveaway. This is my ZID Z5683617. And this is my final submission for the Gravity and Orbits experiment. Over the past few weeks, I've used the PHET simulation to explore how planets orbit the Sun, how their motion is affected by mass and velocity, and how Kepler's laws and Newton's laws explain what we observe in space. In this video, I'll walk through Kepler's laws of planetary motion, dive into some key observations from the simulation, share my results, and finish with what I've learned from the whole experience. Laws. Kepler's first law is the law of ellipses. It states that all planets move in elliptical orbits, with the Sun located at one of the foci of the ellipse. While we often imagine orbits as perfect circles, they're actually slightly stretched out. This law is groundbreaking because it challenged the long-held belief that planets moved in perfect circles around the Sun or the Earth. Kepler's second law is the law of equal areas. It says that a line drawn from a planet to the Sun sweeps out equal areas during equal intervals of time. What this really means is that the planet moves faster when it is closer to the Sun and slower when it is further away. This explains why the Earth speeds up during part of the year and slows down during another, and it ties in directly into how gravity influences orbital velocity. Kepler's third law is the law of harmonies. It describes the relationship between a planet's distance from the Sun and the time it takes to complete one full orbit. Specifically, the square of the orbital period is proportional to the cube of the average distance from the Sun. This law allows us to predict how long a year is on any planet, based on its distance from the Sun. In question 9, I observed that as the Moon orbited the planet also moved. This is because the two bodies actually orbit a shared center of mass, known as the barycenter. In the case of a planet and its moon, this center of mass is closer to the planet, but still outside the moon. As a result, the planet appears to wobble slightly as the moon orbits it. This is similar to what happens with the Sun and planets, but the difference is scale. In the Sun-planet scenario, the Sun is so massive that the center of mass of the system usually lies inside the Sun itself, so the movement is much less noticeable. For question 11, I switched the simulation to 2-scale mode and turned on the grid lines. As you can see in the pictures next to me, the distance between Earth and the Sun is 1 AU. This means that each grid marking is 0.5 AU. The images shown in the previous slide were for questions 12 and 13. I selected 4 different orbital distances by dragging the planet closer or further away from the Sun. After adjusting the velocity vector until each orbit was nearly circular, I recorded the time it took to complete one orbit, and these are my results. As you can see, increasing the distance from the Sun leads to a much longer orbital distance. For question 14a, these results clearly follow Kepler's third law. When the planet is twice as far from the Sun, it takes more than twice as long to complete one orbit. Even though the distances don't increase evenly, the time it takes to complete an orbit increases significantly with distance. For example, doubling the distance from 1 AU to 2 AU results in nearly 3 times the orbital period, from 365 days to 1029 days, which matches the prediction that p squared is proportional to r cubed. The planet with the fastest orbital velocity is Mercury, because it is closer to the Sun and experiences the strongest gravitational pull. This stronger force, it requires a higher speed to maintain orbit. The slowest orbital velocity belongs to Neptune, the furthest planet from the Sun. Due to the weaker gravitational pull at the distance, it can orbit at a much slower speed. This pattern of decreasing velocity with increasing distance is consistent with both Newton's law of universal gravitation and Kepler's third law. This experiment was very helpful in my understanding of how planetary orbits depend on the gravitational force between two bodies. Visualizing Kepler's laws was very helpful as well. I learned that orbital shape and speed are not influenced by a planet's velocity and distance from the Sun, but by its mass. Kepler's laws were demonstrated clearly through changes in velocity and orbital shapes, particularly how orbits become more elliptical when the planet's velocity is reduced. I also gained a deeper understanding of how gravitational forces are mutual and how changing the mass of either objects affects their orbits and movement around the system's center of mass. Overall, this assignment was engaging and it increased my understanding of how our solar system works.